Hello students, we are meeting again for our next lecture of industrial chemistry, and we are discussing manufacture of basic chemicals. Under that, we are discussed this manufacture of ammonia, and in the last lecture we have finished the industrial process for manufacture of sulfuric acid also. And at the end of the lecture we have started the physico-chemical principles for manufacture of sulfuric acid, and especially we are discussing these physico-chemical principles for contact process. And you know that the contact process takes place in three steps. Out of these three steps, the second step, that is conversion of sulfur dioxide to trioxide by oxidation, is a key step. And we have seen in the last lecture the effect of temperature. As the temperature increases, the yield goes on decreasing. The reason for this is the reaction is a exothermic. So therefore, with increase in temperature, it will reduce the yield of the product. So you have to reduce the temperature, but if you carry out the reaction at lower temperature, the yield may increase, but the reaction, as it is a reversible, it does not achieve the equilibrium very fast. So here the reaction can be carried out at lower temperature, and equilibrium can be achieved very fast by using catalyst. And the reaction is carried out at two different temperature, that is 550 degree Celsius and 450 degree Celsius. So that's why while discussing the industrial method, we have mentioned that normally two converters are used. The first converter is operated at 550 degree Celsius, where 80% conversion is achieved, whereas in the second converter, uh, we get 100% output, which is operated at 450 degree Celsius. Now we'll see the effect of pressure. Now, first again we'll see the reaction here. This is the key step reaction where sulfur dioxide is converted to sulfur trioxide. Look at the reactants. There are two volumes of sulfur dioxide and one volume of oxygen, whereas in the product you get the two volumes of sulfur dioxide. That means here the volume in the product goes on decreasing. So if volume decreases, obviously pressure has to increase. So according to Lee Catalier's principle, theoretically we may say that with increase in pressure we should get the uh, more yield of sulfur trioxide, but practically this is not observed. So what is the reason? The reason here is use of catalyst. See, what is the role of catalyst, that you should know every time. Whenever you are using any metal as a catalyst, the metal surface is very important. Okay, so in physical chemistry somewhere you must have learned about absorption, desorption. So what is the role of this catalyst? See, in our reaction the reactants are gaseous. So if you are not using catalyst, the probability of collision of two reactants, and that to a successful collision, so that it will convert to the product, is this probability is very less, because in gaseous state the collisions are less, you can say. And though you may increase the pressure, collision may increase, but that may not be fruitful. So here, if you are using the catalyst, the two gaseous reactants get adsorbed on the surface of the catalyst. They get adsorbed because the surface of the catalyst is an active surface. So when they are adsorbed, the probability of their combination, their collision, their reaction of the reactant molecules is quite high, and therefore when they combine, they will give you a product. Okay, that is going to happen, but the probability has to increase, and that is increased by use of catalyst. Otherwise, if catalysts are not used, then you have to increase pressure, you have to increase temperature, and they are not going, they are just theoretical concept. Practically it is not useful. So when these two are combining, you will get the SO3. But here the problem is SO3 itself is a gas. So if pressure is increased, this gas is expected to get dissolved as soon as it is formed. Okay, when it is dissolved, then only the new entrant reacting molecules will get a good amount of surface area of the catalyst. But here, with increase in pressure, desorption of sulfur trioxide is very less. So here, with increase in pressure, the new molecules of sulfur dioxide and oxygen has to diffuse through the layer adhere to the surface of catalyst, the layer of sulfur trioxide. So it is that means the chances of absorption of new molecules are less, and therefore with increase in pressure you won't get the desired amount of yield of sulfur trioxide. So here, due to this reason, high pressure is not employed. The process, therefore the process is carried out at a pressure of 1.5 to 1.7 atmosphere. So in this way, this physico-chemical principle and practical problems, you can say here, can be combined together, and you can the, avoid the you can say the problem of sulfur trioxide desorption. Okay, so here increase in pressure will not help, so it is carried out at 1.5 to 1.7 atmosphere. Then next parameter, that is physico-chemical principle, is effect of concentration. Okay, so in just now we have seen that equilibrium constant for this reversible reaction as mentioned here. So the concentration term of sulfur dioxide you can see here is the in the square. So you can say that sulfur increasing the concentration of sulfur dioxide in presence of O2 would give you more yield. That is, it will shift the equilibrium to the right hand side, because here sulfur dioxide term, you can see it is at the bottom. So if you increase the uh, concentration term, it will shift the equilibrium to the product side. Now, however, in practice, the aim is to get maximum yield of sulfur trioxide from given amount of SO2. Therefore, oxygen is used in greater proportion. Means here, not only sulfur dioxide has to, its concentration has to change, but the amount of oxygen also needed at the higher level. So here, oxygen is used in greater proportion. Thus, the gaseous mixture which enters the chamber has approximate composition of 8% of SO2 and 10% of O2. Means here you can see the it requires the a large amount, more amount of oxygen, and rest is nitrogen gas, that all of you know. So usually oxygen is mixed with SO2 in the proportion of 3:1 volume. Okay, means here SO2 you can see the square term means 2 times and oxygen is 1 time. So obviously there is totally 3, and 3 out of 3, so it is 3:1. So for each molecule of SO2, sorry, oxygen, there should be SO2 molecule. Therefore the proportion of oxygen to sulfur is taken as 3:1. Okay, because the main reactor is SO2. SO2 has to be converted, so excess amount of oxygen is used here. So that is the effect of you can say concentration. Next is catalyst. Just now I discussed how catalyst works. Catalyst does not take part in the reaction, but it provides the you can say favorable environment. Here the problem is that reactants are gases. So in gaseous state, the fruitful collisions are less. You can study what is meaning of fruitful collision in kinetic theory of gases in physical chemistry. So here catalysts provide the active surface so that it can adsorb the reactant, that is sulfur dioxide and sulfur sorry oxygen. So then only the oxidation will take place from sulfur dioxide to trioxide. So in our discussion we are discussing here the contact process, and for contact process there are two types of catalysts that we are using, and that is first is platinized asbestos. So what is platinized asbestos? Basically asbestos is coated with finely divided platinum, is called platinized asbestos. So on the surface the surface is platinized with asbestos. Then the catalyst can bring 95 to 96% conversion of sulfur dioxide to trioxide at optimum temperature of 450 degree Celsius. Uh, and the activity of the catalyst is reduced with the use, and life of catalyst become short. Means here the platinized asbestos is very you can say efficient catalyst, which can bring about the 95 to 96% conversion, but with prolonged use uh, the life of catalyst becomes short. Means see many times before in this lecture I use the word active surface. Means here active surface means here the ability of surface of the catalyst to adsorb the gases. So slowly with use, extensive use, or you can say prolonged use of the catalyst, this activity goes on decreasing. Okay, so and therefore the life of catalyst becomes short. And here one positive thing about, or positive feature of this platinized asbestos is that though the with use the life becomes short, that of the catalyst, you can recover 90% of original platinum metal uh, by recycling. Okay, so whatever is worn out catalyst is there, you can recover it. And as you know platinum is very costly, so it has to be recovered, otherwise economically it will become difficult for industry to maintain the cost. So there are some disadvantage of this platinized asbestos also. First of all, as I told you, platinum is very costly, so it's costly catalyst. Second is it is difficult to handle. Okay, and third is if the reactants are not purified. We are seeing that purifying unit contains it removes the impurities and purify the reactant. If the impurities, if at all, remain traces amount of impurity, that will poison the activity of the catalyst. So these impurities can be arsenic oxide, arsenic hydrides, chlorine gas, HCl, HF, compounds, various compounds of lead or antimony. They form the film on the surface, and that's why the once the film is formed, the activity get lost in this process. So again you have to recycle. So if at all you want to increase the life of the catalyst, you have to avoid the uh, these impurities to come in contact with the catalyst. So the purifying unit is very important, and it is very essential to purify the reacting gases before entering the contact. So that is the necessity, that is the requirement. So impure starting material will not help to maintain the quality of this catalyst. Then another catalyst which is used, that is vanadium catalyst. Vanadium catalyst, though name we are saying vanadium, it is a vanadium pentoxide. So it is practically they are in, you can say commercially it is called as vanadium. It is very important catalyst. It is very efficient. Okay, as your first catalyst, it is very efficient. Gives high percentage of conversion efficiency. And another important feature of this catalyst is that you can use it for longer period. It has very low initial cost and can be easily handled. There is no danger of poisoning this catalyst. So that is very important feature. The gases need to be purified as in case of platinum. Okay? Means here, though there is no danger of poisoning, you cannot use the let the impurity go along with the reactant. You have to purify, that is inevitable in contact. That is the main feature, and that gives rise to one more advantage, that approximately 100% conversion and 100% output also. The gases, as I told you, need to be purified. However, gases must be free from dust particles and moisture. Means here, uh, the purification uh, quality may be compromised here compared to platinized asbestos. But here also you should avoid the dust particle and moisture. Other impurities, they can be compromised up to some extent as compared to platinized asbestos. So here we can compare both the catalysts by their efficiency, and we get all these points. That is, platinum is high in cost, cheaper in the long run. Vanadium is initial cost is low, also cheap in long run also. And platinum catalysts get poisoned by impurities in gases. There is no danger of poisoning, but in vanadium catalyst you have to take care that at least dust particles and moisture should be avoided. Then platinum catalyst is difficult to handle, vanadium catalyst is easy to handle. Platinum catalyst activity goes on decreasing. Here activity is maintained. Okay. And in platinum catalyst, it can be used for higher content of sulfur dioxide, that is 10%. Here vanadium catalysis cannot be used for more than 7 to 8% of sulfur dioxide. In platinum catalyst, 90% of metal can be recovered from used up catalyst. Vanadium catalyst, though there is no danger of poisoning, but once it is worn out, this catalyst cannot be recovered. It has no value. So this is the comparison of two kinds of catalyst. So depending on feasibility of a particular unit, they can choose the proper catalyst. Chemically, both are very good. So these two catalysts can be compared. So after studying these physico-chemical principles, the favorable conditions for better yield of sulfur trioxides are: temperature you have to maintain between 450 degrees Celsius to 550 degrees Celsius, pressure 1.5 to 1.7 atmosphere, catalyst platinized asbestos or vanadium pentoxide, and proportion of sulfur dioxide to oxygen, that is reactant, should be 1 as to 3. So these are the favorable conditions for efficient conversion of or efficient manufacture of sulfuric acid. So at the end of this sulfuric acid, we'll see important uses of sulfuric acid. At the beginning only I told you that depending on how much sulfuric acid is consumed, your progress indicator is measured. Okay. So sulfuric acid is extensively used in laboratory as well as in industry. That's why we are studying it here under industrial chemistry. Hydrogen peroxide, all of you know, you must be using in lab. It is used in industry also for oxidation purpose. It is obtained by hydrolysis of persulfuric acid. Okay. Which is obtained by electrolysis of 50% sulfuric acid. Okay. So hydrogen peroxide can be prepared by electrolysis of sulfuric acid, which gives you per sulfuric acid, and hydrolysis of per sulfuric acid gives you hydrogen peroxide. Preparation of it is also used in preparation of explosives like TNT. What is TNT? trinitrotoluene. Okay, so at toluene, the methyl group and benzene ring, when they are bonded, it is called as methyl benzene is called as toluene. And this uh, toluene is uh, toluene, if it is nitrated at 246 positions, that is both ortho and one para position, it becomes trinitrotoluene. Then in the same way, trinitrophenol, that is 246 trinitrophenol, which is also called as picric acid. You must have seen the yellow colored solution kept at side rack in the lab. Many times for the testing purpose, you are using that picric acid. Okay. Then nitroglycerin, trinitrocellulose. All these are different kinds of explosives. So, for the preparation of all these chemicals, you have to bring about one important step, that is nitration. And nitration requires not only nitric acid but equally important sulfuric acid, that you are calling it as a nitrating mixture. Concentrated sulfuric acid and nitric acid mixture is called as nitrating mixture. So all of you know the same is required in industry. So most of the explosives are prepared using concentrated sulfuric acid. There are some dyes, like there are different dyes, and for the preparation of those dyes there are different intermediates are required, like nitrobenzene, nitrotoluene, so and sulfuric acid derivatives of aromatic hydrocarbon. So all these can be prepared by using concentrated sulfuric acid. One more thing, that is it is also used as a catalyst. And sulfuric acid is very important catalyst, and it is used in dehydrating agent in esterification process. What is esterification? You know, you must have studied in organic chemistry. What is the general formula for ester? RCOOR. Okay, so is this is ester. This ester is prepared from condensation of acid, that is carboxylic acid, RCOOH, plus alcohol, ROH. So RCOOH group of acid and OH group of alcohol, they combine to form COOR, that is the ester. So in this condensation, the name itself tells you that water molecule is one byproduct. So if and this is a reversible reaction. Due to presence of that water, the ester can again be hydrolyzed back to acid and alcohol. So to avoid, to bring about only reaction in forward direction, you have to remove that water molecule. Then reaction cannot go backward. That is, backward reaction will not be followed if you remove the water, and that water is removed by using concentrated sulfuric acid. Concentrated sulfuric acid is a best dehydrating agent. Okay, then one more use, it is used in manufacture of synthetic fertilizers like superphosphate of lime, triple phosphate, and ammonium sulfate. So here if you see, there are n number of various industrial uh, processes where sulfuric acid is most commonly used, and that's why it becomes a basic chemical, and therefore we are studying it here under industrial chemistry. Okay, so this completes our manufacture of sulfuric acid. Now we'll move towards the next basic chemical, that is manufacture of nitric acid. Now in this nitric acid, we have seen the manufacture of ammonia, we have seen the manufacture of sulfuric acid. So these are extensively. Similarly, nitric acid also, in the lab you must have seen that only concentrated hydrochloric acid is kept on the table. Otherwise, concentrated nitric acid and concentrated sulfuric acid are kept in the window in a tray. Okay, if you need it in for your experiment, you have to go there, because they are very you can say concentrated. These acids are very you can say dangerous for your body. So if it spills, it will cause the corrosion or irritation. Okay, so they are important product of chemical industry. It is used in many industrial product manufacturing. So it is used in synthetic fibers. Nitric acid is used in dye stuff. It is used in explosives. It is used in manufacture of plastic. It is used in manufacture of drugs. Just now we have seen the important uses of sulfuric acid. So sulfuric acid in combination with nitric acid is used in many processes. For example, here just now we discussed explosives. Nitration cannot be possible without nitric acid or sulfuric acid. You have to use it in combination of both. It is also used in manufacture of nitrogen fertilizers like ammonium nitrate or mixed fertilizers like nitrophosphate. So here you can understand why we are studying nitric acid. So we'll start the discussion of its manufacture, and it is manufactured by Ostwald's process, which is also called as ammonia oxidation process. Means here ammonia is oxidized. Now you know NH3. NH3 is ammonia. Ammonia is oxidized means hydrogens are replaced by oxygen, so that it will be converted to nitrogen oxides, and at the end nitrogen oxides are hydrolyzed by water to form nitric acid. It is a, you can say, similar kind of process like sulfuric acid. In sulfuric acid also sulfur is oxidized to sulfur dioxide, then sulfur dioxide to sulfur trioxide, and at the end it is hydrolyzed. Similarly here also uh, the same process is followed, but before that we'll know what are the raw materials for the Ostwald process for manufacture of nitric acid. Very the name itself indicate that ammonia oxidation method means here you need dry ammonia. Okay, then second raw material is air, that is supply of oxygen. Third is water, that is I told you at the last step, you have to hydrolyze that nitrogen oxide, and for this conversion you need the catalyst, that is platinum rhodium gauze as a catalyst. So the reactions involved in this process are there are three main reactions which are involved, which are mentioned here. First is oxidation of ammonia to nitric acid with air or oxygen in presence of platinum rhodium catalyst. Means this is the main reaction where this catalyst is used, that is NH3 is oxidized to nitrogen oxide, okay, or you can say nitric oxide. And this in second step you can see this nitric oxide is further oxidized to nitrogen dioxide, okay, and in the last step that this nitrogen dioxide is absorbed in water, so that it will get hydrolyzed to form nitric acid. Okay, and one more, that if the last step, that is hydro absorption, is carried out in open air, then oxygen and water is used to hydrolyze, and you get the nitric acid by that method also. Here if you observe these three reactions, all the three reactions are exothermic, especially the first one, that is oxidation of ammonia. So all the reactions are exothermic, and you need to maintain the temperature. Okay, so for today's lecture we'll stop here. We'll discuss the further details of manufacture of ammonia in your next lecture, and we'll meet again. Thank you.